All right, everybody, welcome back to Earth Science. Should have already done that part. So we've talked about Earth's revolution. We know that we revolve, which is our trip around the sun, because of these seasonal constellations. Now, how do we know that we rotate? How do we know that this planet is spinning? And how fast is it going? So again, this miles per hour thing I think is neat, but isn't like super critical for understanding exactly how this works. But I like to check it out anyway. And we can do this in Google Earth. I actually did this so that we could do this little experiment here. If I can make my face smaller. There we go. So here's Pulaski High School. Think about this. 24 hours from now, Pulaski High School is going to be right back in this exact spot. The Earth does one spin every day, and it takes 24 hours. So although you sitting in the school, you might feel like you're sitting still. This school itself, if we were to like go out into space a little bit and sit completely still, you would watch Pulaski High School go whipping away to the east, come all the way around, and come back right to where it was 24 hours from now. You're going to make that trip today in the next 24 hours, whether you're at home sitting in your house, your apartment, whatever, is doing that trip. So, how far is it? So, what I did, Google Earth, you can make this. There's a line feature. So, what I did was I started right here and I turned on the grid for latitude and longitude, and I drew that line exactly at our latitude all the way around the planet, which was a frustrating process. But it lets us see, it's kind of neat to see who else is like right on our latitude. So we'll go all the way across the Atlantic Ocean here. So barely scraping northern Spain there, right through the middle of Italy. So I don't know. Sometimes it's just neat. Let's find a town. This town right there, they have our exact latitude. They kind of have our same exact angle of the sun, duration of daylight, how long the sun is up. Everything is going to be the same with the sun because they're on the same latitude. In fact, whatever these buildings are will be there, right, in space, because we're going to go whipping by and whipping around to this town in slightly northern-ish Italy, middle of Italy, northern Italy, right through the Black Sea, through China, northern Japan, all the way back around until boom, we're back in Pulaski. So we make that trip every single day. Then I'll zoom right back into the school. All right, every single day, the high school makes that trip all the way around the planet. So the trick is, and Google Earth does a good job with this, pull up that line and not that line, this line, and look at the measurements, and it tells us there it is, 18,093 miles. This high school is going to travel 18,000. That's not the high school, that's a car dealership. 18,000 miles in the next 24 hours. That's really all we're getting at here. So let's go back. We've got to go 18,093 miles in 24 hours. While you think you're sitting still, you are actually traveling. Well, let's do it. 18,093 divided by 24. That's 753.8 miles per hour. And if you're sitting here in my classroom as you do this, you're heading towards the east, which is right at that wall. So as you're sitting forward, you're flying towards that wall at 753 miles per hour. Fortunately, that wall is also traveling at 753 miles per hour away from you. Okay, so flying, that's going really fast. An important part of where we'll go with Earth science, I don't want to dig too deep into this today. In fact, I probably shouldn't mention it all, but can't help myself. Especially if I forgot how to tilt the Earth. Here we go. As we look at the planet, there's Pulaski's loop right there, that pink line. That's Pulaski's latitude as it goes all the way around. If you look right at the North Pole, somebody's trip around that, they don't have as far to go. So what's up with their speed? Do they have to go faster or slower? Or if you got somebody way out near the equator, they've got to do a longer trip, but it also has to be done in 24 hours. So are they going faster or slower? That's going to get into some stuff we really got to think about when we get to weather and air moving around this planet. That number 753, like this up here, will not be asked. You don't have to memorize that. It's just kind of like, wow, that's pretty neat. We're traveling that fast, but you can let it pop right out of your head right now if you want to. This one, the Regents loves. So you got two paths here. Memorize it today, or always be able to figure it out. I'm not a very good memorizer. I still struggle with your names. When I was in school, I really had a heck of a time memorizing things. But if you can just kind of like think about what is the nature, like how do you do degrees per hour? And you already know both these numbers. So I would like literally write this in the margins of tests and just figure it out every time because I found that easier than memorizing. So how many degrees does the planet have to spin to do that full circle? We all already know that there's 360 degrees in a circle. So if we're looking for something in degrees per hour, I need how many degrees, how many hours, and I'm good. And we do that every 24 hours. And you can grab a calculator then and type those in. 360 divided by 24, and you're going to get to this number, which is a big earth science number that you gotta have in your noggin one way or another. 15 degrees per hour. That's going to come into time zones, which we're not going to get into today. That's going to get into I don't know, a couple other things with the speed of the planets. We move at 15 degrees per hour. Yes, that what I was looking for. It gets into how quickly does the sun look like it's moving over our heads. All right, so back when people thought, okay, we're sitting still, this planet isn't moving, like because it just doesn't feel like it's moving. You're sitting in this room right now, you don't feel like you're moving. Once we realized we were, um, getting to this number, give me one quick sec. So, we thought we were sitting still. It feels like you're sitting still right now. That's not surprising. And they would see the sun going around. Well, they said, well, that must mean that the earth is sitting still and the sun is going around us because I see it rise and set east to west every single day. As it turns out, as we finally figured out that geocentric, earth centered model of the solar system was inaccurate, the heliocentric, sun centered, that's the way it is. And this spinning thing then got to a rate of 15 degrees per hour. But that means that since we're spinning 15 degrees per hour, that's like we see the sun move at 15 degrees per hour, that apparent motion of the sun. We made those plastic globe things for how fast the sun moves, and that's going to be in our next lab, which might even be the last lab of the American period. How fast does the sun move over our heads? 15 degrees per hour. Is it really doing that? No. We're spinning at 15 degrees per hour, but we watch that happen at 15 degrees per hour. So here's some common questions on the Regents. How fast does the sun go in an hour? That's the easy one, 15 degrees per hour. Then they'll get extra difficult, extra fancy, and say, well, how many degrees would the sun go in 2 hours? And you'll have to be clever enough to say, well, if it's 15 degrees per hour, 2 hours would be a total of 30 degrees. Okay? That's really it. But this number has got to be in your noggin, whether you figure it out on the spot or just memorize it today. Extra circle, big star, big star. That's a big one. How do we know that the planet's spinning? I'm actually going to do this backwards. Coriolis effect first. I can post these videos if you want. I got another one that I'm going to put on a full version. These we don't really need audio for. This is one at a museum in Chicago. It's called Foucault's Pendulum. And the idea is if you get a very heavy mass, a very long cable, and you put it on a swivel that can freely go in any direction, that the nature of the earth spinning essentially underneath this pendulum will make it look like it's throughout the course of the day moving around the room. See all these like silver, I don't know, dominoes for lack of a better word? As this museum in Chicago spins underneath this pendulum, it's going to like move and knock down the different ones throughout the course of the day. I'll fast forward way to the end because it takes a while for it to happen. Oh, not yet. Very close. Still very close. There it went. We missed it. But either way, that's how Foucault's pendulum works. I mean, there's a lot of videos if you just want to search some videos on how this thing works. Very slow pendulum, and throughout the course of the day, it deflects, and it has to do with this Coriolis thing, and it has to do with revolution. I'm sorry, rotation. Um, but it was the thing that this Foucault gentleman figured out to show us that we must be spinning, that the Earth must be spinning. So, like this, seasonal constellations shows us revolution. There's this Foucault's pendulum. Even if you can't pronounce that, Foucault's pendulum provide evidence of Earth's rotation. And again, the questions are very literal, like the other thing we mentioned, and like the redshift. Foucault pendulum, rotation, seasonal constellations, revolution. They'll be kind of repetitive and kind of simple, maybe even boring by the time we do a bunch of them. But that's, just like before. If we just practice a bunch of those, when we get to the real quiz, you guys will crush it. Okay? So Foucault pendulum, I guess if we want to say it real quick, shows that the Earth rotates. Keeping straight rotation and revolution is always a trick, but it's a critical trick. We got to be able to get it down. Now, very quick, I don't want to do this a lot today, but Coriolis effects. We're going to have to really get into this when we get to meteorology. The short story is that things bend due to Earth's rotation. Things bend to the right in the northern hemisphere, things bend towards the left in the southern hemisphere, and you would have to flip yourself upside down to see that that is really, as the arrow goes forward, moving to the left. What this creates is large scale systems like high and low pressure systems and hurricanes have a spin one way in the northern hemisphere, another way in the southern hemisphere. There's a misconception out there, and I'm going to show some of these videos, that it makes toilets all swirl one way in the northern hemisphere and the other way in the southern hemisphere. That is not true. It takes a pretty large scale system without a whole lot of other things affecting it for this to really work. The little jets in the toilet have way more of an effect than Coriolis would, because your toilet doesn't cover a ton of latitude from one end of the toilet to the other. It really has to be a pretty large scale system for Coriolis to work. And it works because of our spinning. So if we can just today save the harder part of Coriolis for marking period 2 when we're really getting into weather, I just say Coriolis is caused by Earth's rotation. That's going to be it. And I know that leaves a lot of questions, but we have a lot of work to do there, and it's too much work to cram into this little mini lesson. So, Coriolis effect, this bent path thing, rotation, Foucault pendulum, rotation, speed of 15 degrees per hour. Okay? You'll see the classwork, you'll see that the questions are very repetitive, and you'll do great. Thanks for sticking with me. Good luck.